Good morning, grade 11s. I know it's only been 24 hours, roughly, since we've had our test, our first online test, and I think it went okay. Yeah, I know you're excited to get like straight back to doing physics again, and you don't want to waste any time. You want to get right back to it. I know, like you've been maybe the last 24 hours have been a little difficult without any physics to do. So listen, without further delay, we'll just get right into it. And we get to start a new unit. That's so exciting. Wow, I better fix that typo. It's so exciting that we're starting something new. And the nice thing about it, transformations, there you go. The nice thing about it is that these questions, the stuff that we're about to be looking into, have to do with something that's not totally unrelated to what we were talking about before with like motion and kinematics and dynamics. So that's exciting that we're still doing that. But it's a new way of looking at it, which is always fun. Okay, now there's homework here. Before you get all worried about how much homework we're going to do right now, we're just going to do lesson 1 today, which is right there. Oh, here, I'll do it better for you. This homework, color in. So that's the kind of work you can expect to do, this week. It looks like a lot. It's not very much. There is a worksheet too. I'd say altogether it would take less than an hour to do everything, including the worksheet. It's pretty simple. It's just using a formula in some cases, and some of these cases it's just a quick answer. And we'll talk about that later. But yeah, pretty straightforward. All right, so let's get right to it. What is the definition of work and energy? Well, let's deal with the one you probably know better first. First, what is energy? Well, this one's pretty easy to define. In physics, highlighter, physics, energy is the capacity for work. Okay, so that is what energy is. And I'm going to use my rainbow color, okay, to underline that for you. So energy is the capacity for work. Okay, so you can see there's a connection between work and energy. So if you have energy, you have the capacity to do work. Now, unfortunately, this word work means a lot of things in our society, like I can't go to work today because of the pandemic, right? You can't go to school. Your parents probably can't go to work. So that definition of work, just this place where you go, okay, and you do your work, whatever it is, that definition of work is a very different definition from the physical definition, okay? So in physics class, we want the physical, sort of mechanical definition of work. So physically, what is work? And I'm going to explain that to you right now. Work, okay? Instead of writing a definition by words, well, I'll write it by words. It's the dot product of force and displacement. I'll just scroll over, okay, like that. The dot product, so let me again use my magical rainbow color. It's the dot product of these two things, force and displacement. Now these are both vectors. Well, we've learned how to add and subtract vectors by using, say, the tip to tail method, right? We draw a diagram. But how do you multiply vectors, right? Well, because product implies multiplication, right? Well, it turns out there's 2 ways to multiply vectors, and that's why we use this word dot, okay? Now, let me explain to you what dot, and the other way of writing a product is cross, okay? So in order to explain it, I'm first going to explain it with scalars. Now, scalars are just numbers like 3, 4, 5, 6, no direction, right? So you're familiar with 3 times 4. Okay, and here I'm using what's called the cross notation of a product. So 3 cross 4 is 12, right? Now, 3 dot 4 is also 12. So it's another way of writing a product is to write a dot. Okay, so there's dot and there's cross. So the thing is with scalars is cross and dot just mean exactly the same thing. But with vectors, They're not the same, okay? So let's do number 1, the cross product. So what is, here, let me give you an example. Let's say you have two vectors like this. That's vector A. And then you don't have to join them. You don't draw diagrams for these ones anyway. But I'm going to join their tails just so you can illustrate something. Let's say the angle between them. That's terrible. Let me fix that. The angle between them is theta. Okay? So what's the definition of dot product? Well, sorry, cross product. A cross B, okay? A cross B is equal to A times B times the sine of the angle between them, okay? Now, this result is a vector, and you use what's called the right-hand rule, like the result has to be perpendicular to both A and B, okay? So it's complicated how you figure out the direction, but don't worry about it because that's not what work is, okay? Work is a dot product of two vectors. So what is the dot product? Well, A, and like I said, these are just mathematical definitions. A dot B, okay, so this is dot product, is equal to AB cos of theta, okay? Now this result is actually no longer a vector, it's a scalar, okay? So when you take the dot product of two vectors, the result is a scalar. And this is the formula for how you work out the dot product, okay? Now, let me try to explain to you why work is a dot product of force and displacement. It actually makes perfect sense, okay? So let me refer to this little guy here, okay? So now what we're going to do is we're going to look at work. What do you have to do work? Well, let's say, for example, a student is pulling this box. Okay, let's say Luke here is pulling this box. He's pulling it on an angle. Now, is he doing work? Well, it turns out that yes, he is doing work. But how much work is he really doing? How much physical work? Well, since work is this dot product of force and displacement, what I'm going to do is I'm going to put in the displacement in here. Like he's moved it a certain displacement in the horizontal direction, right? So here's the thing. This vector, this applied force, and I'm going to highlight it here in blue. This applied force, there, that's the applied force that he's doing. So he's pulling, so he is doing physical work, okay? And the deal is there's two components to this force. There's this rainbow one here, okay? And there is another component, I'll color it red, like that. Now, if you use the component method to break down these components, remember this is theta in here, I know it's drawn for you, okay? If we break down these components, then what happens is the adjacent one goes with cos of theta. This is already labeled for you, so I'll just underscore that. That's F cos theta. So that's your applied for it. I called it FA. Okay, your applied here. This is your underscore, and that is your applied force, right? Times the cos of theta. Now this red one here is the applied force times the sine of theta. See, that's the one we would use if it was the cross product. But with the dot product, it's this, what we're going to do is we're going to multiply the rainbow component, F cos theta, times the displacement. See, and that's where the formula comes from. So it comes from, it's force times displacement times the cos of theta, right? Now the thing is like when you think about it, he's pulling it horizontally. So which of these vectors is doing useful work? Well, I'll write it for you here. F cos theta is doing the work because it's parallel to delta D. Okay? F sine theta does no work because it's perpendicular. whoops, I'm having a hard time this morning. Okay, it's perpendicular to delta D. Okay, so that's it. See, like, doesn't it make sense, right? That this red vector isn't really doing any work because it's not really contributing to pulling the object through that displacement. Okay, the displacement's horizontal and that red vector is vertical, so it's not really doing any work. Just like in this picture here, there's two other forces too, gravity, and there's also a normal force. Those forces are also perpendicular to the displacement, and they aren't doing any work either. Only this rainbow vector, okay, only that guy is doing any work, right? So that rainbow vector, very important, f cos theta, I'm gonna circle it. Okay, f cos theta, that's the one doing the work, right? These other guys, not, here I'm just gonna put a little x, not really doing any work, right? But that one there is parallel to the motion, so it's doing all the work. Okay, now, just to summarize all this, okay, now I'm just going to get to it. So hopefully I've sort of established to you how we figure out work. Work, then mathematically, work equals the dot product of force and displacement, which I already told you, definition is the force times the displacement times the cos of the angle in between. Now, these are magnitudes, so we don't even have to worry about the direction. The only place where the direction really matters is right here with the cos of theta. So that's the angle between them. So that's where the direction sort of factors in. Okay, and it is possible that cos of theta is a negative number. Okay, and that's when you're taking energy away from your object and not giving it energy. So we'll talk about that when we do more examples. All right. So now that's the definition of work, very straightforward, right? So let's do an example. Okay, how do you do questions involving work? Well, it's very straightforward. Okay, this question was on a test last year. All right, so let's say, oh, actually wait, before we talk about the example, let's talk about units. What are the units of work? How do you measure work? Well, pretty straightforward. The unit of force, you know, is newtons. The unit of delta D, of course, is meters. So therefore, putting these together, the unit of work should be Newton times meters. But we've named a unit of work in honor of a scientist. So what we say is 1 joule of work equals 1 Newton times 1 meter, right? So you understand, therefore, 1 Newton meter equals 1 joule of work. So joule, you know that unit, that's for energy, right? Well, now you know what a joule is, okay? So therefore, a joule is the amount of work done when 1 Newton force is applied to an object that moves 1 meter. Okay, and that is the definition of a joule. Okay, so hopefully that makes sense. Like 1 Newton is about the weight of an apple. Okay, so, and here's the thing, if you take the apple and you just push it 1 meter, and you push it with 1 Newton of force, yeah, you've done 1 joule of work. And we use the same units for energy because that's going to cost you 1 unit of energy to do that, like 1 joule of energy to do that. So you know you had a bowl of cereal this morning, had 1,000 joules in it. Well, you know, you've just used 1 of them to pick up that apple, right? And that's it. Okay, so that is the definition of a joule of work. And now let's do our example. Okay. So number one. All right, let's say you have this mass. Let's make it like our picture. Okay, so let's say the applied force here is 15 newtons. And let's say the displacement is this way. Okay, and the displacement is 5 meters. And let's say our angle here, theta, between the force and the displacement is 30 degrees. Okay, so the question is, how much work is done? Well, work will just equal 15 times 5, right? Force times displacement times the cos of 30. Okay, so I just multiplied out. 15 times 5 is, whatever that is, 75 or something, right? So 15 times 5 times the cos of 30 is, like a 64 point, or around 65 joules, approximately 65 joules. Okay, so 65 joules of work to do this. Okay, 15 newtons pulled for 5 meters on an angle of 30 degrees. You're going to do 65 joules of work. And that's it. Okay, so that's a very simple example of work. Let me give you a second example. This is a lifting example. How much work does it take to lift something up? Well, let's say you have a 12.5 kilogram mass. That's about 25 pounds. Okay, so let's say you have a mass, okay, where your mass is equal to 12.5 kilograms. Well, when you lift something, you're fighting gravity, right? So this is your applied force. This is the force of gravity like this. Let's say the acceleration is 0. Now that doesn't mean it's not moving. You're moving at a constant velocity, okay? So we're going to keep it simple. We'll keep the acceleration 0. If it wasn't 0, your applied force would have to be greater, and then you're doing more work than is necessary to lift something. So let's say you're lifting weights. You've got a 25-pound weight, or 12.5 kilograms, and what you're doing is you're just pushing it up, okay? And you're going to push it up, let's say, a distance of 1.3 meters, okay? Now we're going to call this distance h, okay, for height, and they do that in the textbook too. All right, so how much work is done this time? Well, it's only, I'm going to circle it, it's only, this force here is doing work. Gravity is doing work too. In fact, the object doesn't gain any speed, but you gain gravitational potential, but we'll talk about that later. How much work are you personally doing? Well, we only have to consider this force here, okay? Now, since the acceleration is 0, what we know then is that the applied force is equal to the force of gravity. This is because the acceleration is 0. So therefore, your applied force is mg. That's how much, look, that's how much effort it takes to lift something, right? You have to at least match its weight, okay? And then you'll be able to lift it. So therefore, the work done, okay, that applied force is straight up, h is straight up, so theta is 0. Theta is 0 degrees, okay? So therefore, work is equal to force times displacement times the cos of theta. That's going to equal mg, okay, times h. And the cos of 0, students don't get this. I'm going to circle this in red. Cos of 0 is not 0. Just take out your calculator and go 0 and press cos. It's 1. And that's whenever theta is 0 degrees, you can just write force times displacement. You don't have to write the cos of theta, because cos of theta is just 1 if theta is 0. Okay, so anyway, I'm going to write this. This is just equal to 1. Okay, and so therefore, I'm not really canceling it. I'm just replacing it with 1. Therefore, this is equal to mass is 12.5 kilograms times gravity is 9.8. Okay, and then times h is 1.3. Okay, and what do I get? Well, 12.5 times 9.8 times 1.3 is 159.25, so 159.25 joules. Okay, so your bowl of cereal is getting, you know, that energy you got from your bowl of cereal this morning, well, you're using it up, okay, lifting that weight. Now, if you do that a bunch of times, if you do that 10 times, and in a set that has 10 reps, or you're lifting it 10 times, well, that's how much work you're going to do. Now, if you're wondering if you're doing any work when you're lowering it, you're not, because what's happening is gravity does the work there. So you do the work to lift it, gravity does the work to lower it. Okay, that's why it's easier to, let's say, move something down compared to moving it up, right? That's why you get more tired climbing a hill than you do going down a hill, right? Because you're working against gravity there. You can let gravity do the work when you're coming down. So there, that's how you do a problem when you're lifting it. Okay, so anyway, that's the mechanical definition of work. It's very simple. Okay, so we measure work in joules. Okay, so in both of my examples, I've got my work done in joules, and it's just a formula, and I will circle with the rainbow the most important formula here. That is your formula for work. Okay, now let me give you a break on some of the homework here. I have a worksheet. Okay, so here's your worksheet. And the worksheet, very straightforward. Okay, a 20 Newton pomegranate is lifted at a constant velocity. So this is your force of gravity. Okay, 20 Newton is a massive one that's like the same as 20 apples. Okay, it's lifted at a constant velocity from the floor to a height of 1.5 meters. I guess somebody dropped it, right? How much work is done on the object? So here you would go, whenever you're lifting, you would say the work done is mgh. Or, let me change that because they don't tell us what the mass is. You don't really need to find it. You can just go fgh. So that would be 20 times 1.5. So easy, right? Super easy. Okay, so now let's look at, let's skip to one, number 6, okay? A 60 kilogram student runs at a constant velocity up a flight of stairs. The height of the stairs is 3.2 meters. What work is done against gravity? See, when you climb stairs, the horizontal movement, doesn't require any force really to move horizontally. It's the vertical movement you're fighting against gravity. So we don't really care that you're moving up the stair as you're going horizontal at the same time. We don't really care. We're just going to do it like this. The work done is mgh. Super easy, right? Whenever you're lifting anything, going up, okay, that's it. Now, what about number 2? A 15 Newton potato is moved horizontally, okay, 3 meters across a level floor. Well, that's one of these. So what's happening is you're applying a force of 6 newtons like that. These forces here, normal and gravity, we don't care because you're moving this way. So they tell you this, that's a red herring, you don't really need it, okay? But we do need these other numbers. So the work done here would be 6 times 3, and the cos of 0 degrees is 1, and so that's 18 joules of work. Super easy, okay? Yeah, anyway, that's it. I'm going to let you do this. It's honestly, this homework, like I did 3 questions here. Those 3 questions took me less than a minute, okay? So if you know what you're doing and you just use the formula, you're good. Remember that if you're fighting gravity, like in question 8, for example, okay, an 80 kilogram is pushed up at constant velocity along a frictionless plane. How much work is done on the pumpkin moving it up the incline? When you're climbing anything, you're fighting gravity. So the only thing that we care about is this h. So again, here, all you have to do is the work done is just mgh. This number here is a red herring. Okay, we can ignore it. Okay, now in real life, we always have lots of numbers that we ignore. So, but in these questions, people get confused by them throwing in numbers that you don't need. Okay, so anyway, I think you can see this is very straightforward. This whole worksheet here just takes really 10-15 minutes at maximum, and the questions in the textbook, same. Okay, now some of the questions in the textbook are a little unusual. Okay, I defined energy for you, okay, as the capacity to do work. Just let me finish this video by saying this. They have these things called energy transformation equations. So let's talk about that just for a moment. Energy and work. Whenever you do work, energy is changing forms. So we'll talk about forms of energy. Okay? So what forms of energy can you think of? Well, because we're not having a conversation, I'm just going to tell you. There are several different forms of energy that we can talk about. One of them is kinetic energy. So anything that has energy can do work. Well, if you were hit by a ball, could that ball exert a force on you? Of course it could, right? If you're playing dodgeball. So dodgeball, when the ball hits you, it exerts a force and it could cause you to displace. So it can do work. So because the ball, because it's moving, has the capacity to do that, then it has energy. And we call the energy of a moving object kinetic energy. Okay. Gravity can do work. It can exert a force on a moving object, right? So we call this gravitational potential. Chemistry. Chemical bonds have energy that we call chemical potential. Electric potential. Electricity can do work, right, on something. What else? Elastic potential. So let's say you have a bow and arrow in your hand, right? And you draw back the bow. When you draw back the bow is elastic. Elasticity means the tendency of an object to reform its shape when you deform it. Okay? So you take your bow, you stretch it out, and then when you let it go, it's going to reform its shape. When it does that, it can do work. And it'll do work on the arrow and give the arrow kinetic energy. So what's happening is elastic energy, when you stretch a spring or a rubber band or something like that, you're storing energy in it. And then when you release it, that energy will change forms. Okay? So here's a short list. I guess we could say nuclear potential. That's energy stored in the nucleus of an atom, let's say. Thermal is a form of energy. It's actually a form of kinetic energy. Thermal and kinetic energy are very closely connected. It's kinetic energy of the molecules in a substance. It's called thermal energy. All right, let's just leave our list there for now. We could probably think of others, but that's good enough for now. Now, what they do in the textbook is they say transformation equations. See, whenever work is done, energy is changing forms. So for example, if I drag a box across the floor, okay, there's my body has potential energy in it. It's chemical potential, like I eat food. Okay, so it's chemical potential energy in my body. When I drag the box across the floor and the box starts to move, I'm turning the potential energy in my body into kinetic energy in the box. Okay, and so there's a transformation going on. One type of energy turning into another. And in physics, it's happening all around us all the time, right? I guess I should say radiant energy too. Like light is a form of energy, right? Okay, so radiant energy, can't forget about that one. All right, so in a transformation, the textbook will say, what's happening in a bonfire? So let's use that as an example. Okay, in a bonfire, what kind of energy is in the wood to start with? Well, the wood has chemical energy in it. It's bonds, okay, chemical bonds. And what happens is when you burn the wood, what does that turn into? Well, one of the things it turns into is light. So that's radiant energy. But another thing it turns into is heat, which is thermal. In other words, everything gets hot, okay, around the fire. Thermal energy. And then sometimes pieces like a spark will go flying out, and that is kinetic energy in the fire. Okay, so what's happening is this is called a transformation. It's not really an equation, but this is called the energy transformation process. Okay, where one form of energy is converted into 3 different other forms of energy. Okay, and that's what happens at a bonfire. Okay, so here this is light, this is heat, and this one here is particles particle motion, I guess I should say. So sometimes little cinders and stuff come flying out of the fire. Okay? So that's it. That's a chemical transformation equation. I didn't want you to get, or sorry, an energy transformation equation. I didn't want you to get confused by this. Let's do another example. Okay? Let's say a bow and arrow. Okay? So in a bow and arrow, what's happening? Well, what happens is you draw back the bow. Okay? So you start with elastic energy in the bow. Okay, now what does it become? Well, when the arrow shoots off, it moves, so it has kinetic energy. And this is in the arrow. Now, one thing that it doesn't, that the book will mention to you, is every time something like this happens, there's also some waste. And it's always in the form of thermal energy, so we call it waste heat. And it's a rule, you always get that. In other words, when you have a machine that converts one type of energy into another, like a bow and arrow, you always get some waste, okay? And so waste heat is just a normal sort of thing. The reason why waste heat happens is because of something in chemistry and physics that we call entropy. You always get waste heat. It's a law in physics that whenever energy changes forms, waste heat is created in the process. In other words, some of the energy dissipates out into the environment in this form called waste heat, and that's just completely unavoidable. It's how our universe is. Okay, you always get waste heat. And that's why, like for example, let's say you're swinging on a swing where gravity and kinetic energy are being exchanged. Well, if you don't push yourself on the swing, if you don't like rejuvenate the energy, okay, you're going to slow down and eventually stop. So that's waste heat in action, right? The reason why you just swing less and less and less on each subsequent swing is because of waste heat. All right, that's it for now, guys, and I hope you have a great Easter weekend. If you have any questions, I spelled entropy wrong. If you have any questions, don't hesitate to ask. It doesn't matter if it's Easter weekend. It's up to you. Like whenever you're working on your work, I'm okay to answer questions. I might be busy too, but I'll get to it. All right, guys, so enjoy yourself, and please, for homework, please do lesson 1 in the homework outline. And like I said, it looks like a lot, but trust me, it's not, okay? If you do it, you'll see what I mean. So lesson 1 in the outline, and then here, this worksheet, I've already basically done 4 of them for you. There are 10 questions there. Those 4 questions took me less than 2 minutes. So it's really not a lot. So I'm trying to give you a break this week because we had a test. So our pace is a lot slower with this whole distance learning thing. That's fine. Okay. So go ahead and do it, and have a good weekend. We'll talk to you soon.